I'd like to begin with a new topic today. So far we've been talking about semiconductor materials, and as I mentioned in the introduction, electronic materials don't consist solely of semiconductors, and the course, while it laid an emphasis on semiconductors as one of the most important class of electronic materials, we have some other materials to consider also. And so what I'd like to do today is to talk about dielectric materials. And predominantly the materials that we will consider today are ceramic materials. The word dielectric conjures up an image of being able to store charge. Okay, that's basically what a dielectric material does. It's able to store charge in addition to some other things that we will look at. In another context, it will be an insulator, its ability to prevent the flow between two conductors. But in this context, we're going to look at its capability. How good is it for storing charge? In other words, in circuits, when we use things like capacitors and so on, we need dielectric materials. And in addition, some of their properties are made use of for things like insulation. Some of these materials also exhibit very interesting properties like piezoelectric effect and the ferroelectric effect and so on. Time permitting, we will look at some of those. But I'll give you a quick introduction in, say, 2 or 3 lectures to what are dielectric materials. Let's begin by considering a parallel plate capacitor. All of you are familiar with this in varying degrees. If you have 2 plates separated, each plate having an area A, and the separation between the plates is D, and we connect that up to a voltage source. And in this, right now there is nothing between the plates, it's just free space, and in that context we can write that the capacitance of such a system, a parallel plate capacitor, is given by epsilon naught A by D, where we have that epsilon naught is the permittivity of free space, or the absolute permittivity. Note that it depends on the area as well as the separation between the plates, and then this is something that has to do with the medium between the plates. And C is the capacitance, which we will define as capacitance is the charge storage ability per unit voltage. For that system. Now what happens if we replace, put in over here something which is a dielectric medium? And when we put that in and it is capable of holding charge, so we now have a system. I'm not going to draw the details, but in cross section it will look like this, and it's of course still connected to our voltage source, which is applying voltage V. And this has got the ability to store charge, and when we insert that there, then our capacitance changes so that it is now epsilon R epsilon naught A by D, where epsilon R is equal to epsilon naught. Epsilon by epsilon naught, sorry. In other words, this is the relative permittivity or the dielectric constant. So as you can see, it's when we have replaced what was free space by a dielectric medium, our capacitance has increased by this term, which is a measure of the ability of the material to store charge. So we talk in terms of K or epsilon. In different books, different notation is used, and you'll have high K materials, low K materials, which is very popular these days, even in the semiconductor industry, as the dimensions of the devices shrink, and so we talk about high K and low K. The same K refers to this epsilon R, which is the dielectric constant. Now, why has the capacitance in such a system increased when we put in this slab? The basic phenomenon that is involved is called polarization. I'm just doing a quick review, quick introduction, and then we'll go into some of the details. And polarization involves the formation of dipoles. So the medium gets polarized, by the formation of dipoles. And what are dipoles? In this context, we can talk of different kinds of dipoles, but these are electric dipoles, where we have two charges of equal magnitude and opposite sign that are separated by a certain distance. If we call that A, and the charge is Q minus and Q plus, then we created a dipole. So they have got the same magnitude of charge on them, the sign is different, and they're separated by A. So in other words, to have a capacitor, we must have a material that is capable of forming dipoles or capable of being polarized. For a dipole, we define what is known as the electric dipole moment, which has the symbol P. And P is simply defined as the charge multiplied by the separation. Now, when we formed this dipole in a material, the net charge is still 0. But there is now an electric field that is set up within the material, which can interact with the internal field. Now, there are different mechanisms by which materials can store charge, and we will look at the details of those mechanisms later. But what I'd like to point out here is that the charge storage mechanisms have a frequency dependence. So in other words, something which is good for storing charge at low frequencies may not be suitable for storing charge at high frequencies, and vice versa. So we tailor the materials and the devices according to the needs that we have, depending on what frequency range that we are operating in. So there's a frequency dependence to the ability to store charge. And there's also a frequency dependence to something called the losses. Now, much like a resistor, where you have I squared R losses in the resistor, there are losses in a capacitive system too. And in that context, these losses too have a frequency dependence. And we will look at this also, the frequency dependence of the different mechanisms that allow this capacitor to store charge, as well as the frequency dependence of the losses. Now, as I mentioned earlier, capacitors, these dielectrics, not only store charge, in addition they are able to serve as an insulator between conductors. And in that sense, there's going to be some critical field above which they will break down. Okay? They simply cannot indefinitely sustain any field that is applied across them. All media will ultimately break down. And a classic phenomenon that we see is lightning, where the air is breaking down and we have a conducting path from the clouds to the ground. Similarly, any material has got a breakdown field, and there's some critical value that it can sustain. So the critical field above which breakdown occurs is referred to as the dielectric strength of the material. Okay, so we'll look at that also, why they break down and so on. But this is another property of a dielectric, in addition to its ability to store charge, up to what field can it sustain before it breaks down. Okay, these are some important parameters that relate to dielectrics. Actually, more than 40% of power generation plant failures relates to dielectric breakdown. So it's a very critical phenomena, because for various reasons localized fields may be set up that are beyond the ability of that medium to sustain, and we get breakdown. So it's a very important phenomena to understand. Now I'm going to take up what I just discussed, namely the charge storage of a capacitor and its breakdown in more detail in the next minutes that we have. Let us begin with a definition of what is relative permittivity. If you recollect, I just showed that when we put in the dielectric into the parallel plate, between the two parallel plates, capacitance has gone up, and I said that this term epsilon R is the relative permittivity. The ability to store charge has increased by that much. And when we do this, we see that it can also be, well, I'll come to that in a second, the proper definition of that. But let's begin again with the plates as they are. connected to a voltage source, V. And what we find is that charge is set up on the plates, plus and minus Q naught, and there is a field between these. That's the setup we have before we inserted anything. And if the charge on the plates is Q naught, which we will come across later again, and the separation between the plates is D, we can write also that the capacitance C naught is equal to Q naught by V. Now, Q naught is something that is measurable. What is the charge on these plates is something that we can measure. And so we, in terms of measurable quantities, we have now defined what is the capacitance when there is no dielectric medium. Also note that the field, which is defined as minus dV by dx, in this case is nothing but V by D. You've got a potential V applied, and so the field is nothing but V by D in this case. So this is the case when we started off looking at there's nothing between the plates. Now we insert something, a dielectric medium, between the plates. We bring it in. And we have the same setup as before. Except now we see that when we are inserting it, there is a current flowing in the circuit. Okay? So we have a current which is a function of time starts flowing in the circuit. And the charge that has been stored on the plate has changed from Q naught to Q. Hold on, plus something like that we have to have. So we have changed our charge storage from Q naught to Q. This is still a measurable quantity. Current is flowing in the external circuit because this extra charge has come in as a result of introducing the dielectric medium. And we know what is this charge by measuring the current in the external circuit and integrating it. That's all we need to do. Then we will know how much has the charge changed, basically. The capacitance then has changed from C naught to C. We had C naught earlier defined by Q naught by V, and now we have C, which is equal to Q by V. We can now define the term epsilon R is equal to Q by Q naught by how much has the charge changed, the ratio of the increase of charge, or also as C by C naught, V remaining the same. This is the basic definition of relative permittivity. When we introduced it into the system, by how much has the charge changed. Okay? Relative permittivity. So this is a measurable thing because I can measure the charges, and so this is something that is a macroscopic quantity that I can observe and measure. Note also that as long as the medium that we are inserting fills the space completely between the two plates, the field remains the same because we are still dropping voltage V across a distance D. D hasn't changed as long as we fill up that space, and the whole voltage is now still dropping between these two plates, given that the medium is filling the whole gap. So the field is still remaining as V by D, even in this case when we have inserted something into between the plates. Now we have already mentioned this term. I'll bring it up again. Dipole moment. So what happened when we inserted it, the dielectric medium, is that dipoles were formed, and I said that that phenomenon is known as polarization of the medium. The dipole moment P was defined as the charge separation times the distance between them. And if we have two charges, a negative charge and a positive charge, separated by a distance A, then the dipole moment is simply given by QA. Note that the dipole moment is actually a vector directed along A. A is in the direction from the negative charge to the positive charge. So we have a dipole moment directed from the negative charge to the positive charge. So I'm just introducing a few terms as we go along. Now there are different ways in which a material can exhibit polarization, but one of the fundamental ways that is common to practically all materials is what is known as electronic polarization. There's no net charge within a material. And basically, if you look at an atom, on an average, the positive center coincides with the center for negative charges, on an average. for a given atom. But what happens when we put, so in other words, there is no net charge on the material, and then there is no net dipole moment either, because these two are coinciding with each other. The centers of positive and negative charges are coinciding. But when we apply an external field, what happens? The electrons being lighter than the, much lighter, about what, 2,000 times lighter roughly, 1,800 and something, 40 times lighter than the what? The proton, right? But you also have, no, than the neutron. Basically, it's the point I'm trying to, 1,840 or whatever it is the electron is significantly lighter. And so in the presence of a field which we have applied, we end up getting a displacement of the negative and the positive centers. Because we have applied a field, one is able to move much more with respect to the other, and we end up creating dipoles and dipole moments. So this is the situation after we've applied. The center of the negative charge is somewhere here, the center of the positive charge is here, and we've created a dipole. And this is called an induced dipole moment. The P that is there is known as induced dipole moment. And we can say something about its relationship to the applied field, namely that the P induced is equal to alpha times the field. We'll see that there is it's proportional to the field is the basic idea. You increase the field, you increase the dipole moment that is induced. What is alpha? Alpha is known as the polarizability of the atom. Now this polarizability depends on the particular mechanism. There are many mechanisms, as I said, by which the atom can get polarized. In the specific case of electronic polarization, the symbol we will use is alpha subscript E, where we are talking specifically about electronic polarization. This is a microscopic quantity relating to sort of at an atomic level what is happening, atomic or molecular or microscopic level, what is happening within the material. Remember, epsilon r here that we looked at, the relative permittivity, is something that we are observing at a macroscopic level. How has charge that is stored in the material changed? How has capacitance changed? That's what we are looking at. Whereas what we can understand out of alpha is what is the particular microscopic mechanism that is responsible for polarization. And my goal is sort of to relate some of these quantities as we come towards the end of this lecture or in the subsequent lecture, whatever time allows us. Basically, all atoms in varying degrees possess electronic polarization or can be electronically polarized. This is one mechanism that is more or less common to all materials, though in varying degrees, some more so than others. And so what we'll do is for some time we'll focus in on this electronic polarization in a little more detail. Let us consider an atom with Z electrons. Okay, so we've got Z electrons, and these Z electrons are within a spherical area, some defined spherical volume around the nucleus. These are some approximations, obviously, but it's there. All right? Around like these. As before, when we apply the field, we create dipoles. The centers of the negative charge now are separated, and we've got a dipole that is created. The electric field is E. So there is a field that is, there's a force that is trying to separate the positive charge and the negative charge. Now, when you have a positive charge and a negative charge separated like this under the influence of the electric field, what else can you imagine might be a force acting on these? Coulombic attraction, right? You put a positive charge and a negative charge near each other, there's a Coulombic attraction. So in addition to the field that is applying a force on them to separate them, there is a Coulombic attraction that is restoring them. All right? So we've got a restoring force due to Coulombic attraction. Now we can write the force due to the field as ZE, which is the total charge times the applied field. Similarly, the Coulombic restoring force can be expressed as some constant times x. It's a function of x. It's like a spring, if you remember, the force. Okay? When you take something and pull it apart, the restoring constant, we have a spring constant. When you have two masses suspended by a spring, we call that what, k, or some symbol is used there, and we say kx. The restoring force is a function of?
That used to be Z E square by...
Yeah, that is another way of expressing it too, in terms of the distance like that. Yes. This is, if you imagine now that these are like suspended on a spring, there's a bonding between them. We can write the restoring force then in terms of some constant d beta times x. That means it's a function of x, basically, what we're writing. Okay. Whereas beta is some constant. I'm not worrying about it. So this is the restoring force, and we will then equate these two to get Z E, magnitude only we are considering, beta x. And the minus sign indicates that the force is directed, is from the negative charge to the positive charges. So out of this we can then extract, or before that, we know that the polarization is given by Z E x, charge times the separation. So in this case it's simply ZEX. So I have an expression that I can substitute in here. Okay, ZE is the total charge. I'm going to substitute for ZE here in terms of, no, I'm going to substitute for, hold on, I'm going to substitute for x in terms of ZE, epsilon and beta. So we're going to make a substitution for x here in terms of ZE, epsilon and beta. And when we do that, we get that the electronic polarization is equal to this ZE times beta x by epsilon, and by the field, electric field. Did I get that right? Sorry. ZE E by, what am I writing? The opposite I've written. ZE E by beta. Thank you. This is what we have. So we can write that as what? Z squared E squared by beta. All right. Now note, in the beginning itself I said that the polarization is proportional to electric field. And what we had was defined a term alpha, the polarizability. And when we compare these two equations, we see that alpha E in this particular case, electronic polarizability, is equal to Z squared E squared by beta. Okay, that's what is the electronic polarizability that we have, the P being proportional to E. Now what we have here is valid under static conditions, namely DC. Okay. Now what we can do is to consider what will happen if I suddenly remove the applied field. At that point, which is the only force that is active, is the restoring force. So it's now going to swing back, and there's going to be like the spring action, a simple harmonic motion that is going to be executed. And when charges are moving, you have from quantum ideas, radiation of energy. So eventually this is going to die out, right? So it will swing back and it's executing simple harmonic motion, and eventually it will die out and settle down to some equilibrium condition. So when we looked at, I removed the applied field suddenly. Only this beta x is active, right? So it will swing back and execute simple harmonic motion. Now we can look at it in terms of the equations of motion. F is equal to ma, all right? And what we would like to see is what is the force acting on this when it is moving is equal to what is the mass, z, times each electron's mass, times an acceleration. We've got this is the total mass times an acceleration, which can be expressed by d2x by dt squared, where me is the mass of each electron. So the force that is acting is expressed as beta x minus beta x. It is also expressed as z me d2x by dt squared. We can equate these two and write minus beta x is equal to z me d2x by dt squared. And if we solve this for x, we can get an expression for the displacement as a function of time as x naught cosine, this is a simplification, where x naught is the displacement at time t is equal to 0. That means at the point at which I turned off the electric field, that means at their maximum separation. Exactly. That is an expression of amplitude and how it is. So, in other words, in this particular case, x naught is the point at which I left it. The electric field had separated it by a certain distance, x naught, at which point I switched off the electric field. So, that is the maximum value, which we call the amplitude. Omega naught is a combination of some of the other factors and is given by beta by z me to the power half. It has the units of frequency. That's why we've used the symbol omega. And basically it is the oscillation frequency of the center of mass of this negative charges. They have their center of mass separated from the positive charges as it swings back and forth in simple harmonic motion. Okay? So it's an oscillation frequency for the negative center of negative charges. We can rewrite this equation to get an expression for beta, which we will use later. Beta is equal to omega naught squared z me. And as I mentioned, these oscillations eventually die out because the charge that is in motion there is radiating energy, and so gradually the oscillations die out with time. So now going back, I can write what I had an expression for polarization or the dipole moment as z squared e squared by beta e. This is what I had. And I can make a substitution for beta here, right? And write it as z squared e squared by omega naught squared z me. And therefore PE is equal to Z E squared by ME omega naught squared epsilon. Right? Or not epsilon, the field, whatever be that symbol, I often confuse it. Now looking back, we also had an expression for alpha in terms of beta. We could substitute either directly the value of beta that we have, Or we can make the comparison that PE was equal to alpha E and write then that this term is alpha E. So we can write that the electronic polarization alpha E is then simply Z E squared by ME omega naught squared. Okay? Because we substituted for that beta in terms of the other terms, in terms of other values, and we got this. Now I'll introduce the polarization, which I briefly mentioned, and we'll talk of a polarization vector. We begin by visualizing what happens inside the medium when we apply a voltage. So I've got the two plates, the dielectric medium filling the gap between the two plates, and we are applying a voltage V across this. When we do that, I've got positive charges on the metal plates, okay, and the charge is then plus Q, and on the negative one I've got minus Q. These are two metal plates on which the charge is there. And inside the dielectric medium then I create dipoles. Okay, with the field acting this way. Just drawing a few there. Okay. So the material is polarized with these dipoles acting in this way. Note that all the induced dipole moments point in the same direction, namely this direction, from the negative to the positive. So all the induced dipole moments are pointing from the negative direction to the positive direction. Now if we consider, forget about the metal plate for a second and consider only the dielectric medium. So I've left out the metal plate for a second, and we're looking at what happens to this. We have got the dipoles as before, which I will not bother to sketch all of them in, but just to give us an idea. Minus, minus, plus, so on. And when we look at this material closely, we will see that in the interior, if we are just looking at this, in the interior, you know, this and this neutralize each other. There's a positive and a negative out there. This and this neutralize each other, and so on. But on the surface, on one side, we've got a negative charge. It's a bound charge. It's not moving anywhere as such. And on this side, we've got a positive charge, which we will label as QP plus and QP minus. In the bulk, they are neutralizing each other. On the surface, we've built up a negative charge here and a set of positive charges here. And if you forget about everything else, you can simply draw it as the dielectric now has got minus QP on this plate, plus QP on this plate, and the separation is simply D. And these charges are bound inside the material and are called surface polarization charges. Each of the two surfaces has got an area A, this side and this side, and we've got a separation between them of D. So QP is the surface polarization charge. Polarization, the term with the symbol P, it's a vector basically, refers to the total dipole moment per unit volume. Okay. So basically I can write that this vector P consists of the sum of the individual dipole moments in there. So many dipoles were there. n dipoles, let's say, per unit volume, by the volume of the material, where P1, P2, P3 are the dipole moments of each of the individual dipoles that are within there. I can write it, let us say that each of them has got some average dipole moment, P average. Okay. So then we can write our polarization vector as being n times P average, where n is the number of molecules per unit volume. Number of molecules mean number of dipoles per unit volume effectively. Okay, we've expressed it in terms of a P average. And if these dipoles that are created are due to an applied field, then our P average is nothing but our P induced, which we saw earlier, is if for externally applied field. We make the distinction here because we will see that sometimes there are spontaneously induced dipole moments in materials, not due to an external field. So what I need is, in order to be able to calculate this P polarization, I need the sum of these, and I need to know the volume. The volume is easy. It is simply A times D. Each surface there had an area A, separation is D, I know the volume. But I want the individual dipole moments or an average or something I need. And one way of simplifying this whole thing is to think of it as, instead of individual dipoles, as one big dipole separated two sets of charges, QP plus QP and minus QP, separated by a distance D. That's basically the whole one big dipole, which consists, of course, of all these little dipoles, all pointing in the same direction as I pointed out. Okay? So I can calculate what is polarization by knowing QP and the separation between them. So I can write polarization then as equal to QP times D. That will give me the total dipole moment, sum of the dipole moments, divided by the volume, because polarization was defined as the total dipole moment per unit volume. We are left with QP by A, where QP by A has got a significance. It's called sigma P, where sigma P is also known as referred to as the surface polarization charge density. Surface polarization charge density. So then I can write that polarization P is equal to simply sigma P. Okay. Fundamentally, in this case, when I write it as sigma P, I'm not having the direction there, just the magnitude of the vector. If we are looking at a rectangular slab, and we are considering that the polarization vector is into the negative side, coming into the material, and out of the material on the positive side. That's for a rectangular slab. If we make a broad generalization without going into the details, we can then write that the charge per unit area appearing on the surface, this is just a generalizing statement without going into the details, of a polarized medium is equal to the component of polarization normal to this surface. Okay. In other words, this is defined as what? Surface polarization charge density, charge per unit area. In this specific case, it is referring to rectangular slab, and in that case we saw the field applied across it. We've got the polarization into the dielectric on the negative side and out on the positive side. Making a generalization, we can say that the charge per unit area is equal to the normal component. So if the surface is not a flat rectangular slab like that and so on, we make that it's equal to component of polarization normal to this surface. So sigma p is equal to p normal, where p normal is the normal component of p. Whatever be the polarization vector, its normal component will give me the charge density or charge per unit area. We noted that the polarization P induced, or I'm sorry, the dipole moment was proportional to the field. We saw that earlier through, I'm just writing it, in the case of electronic polarization, PE, we had this expression. We saw this earlier. Similarly, our polarization is also proportional, dependent on field, I should say. And the expression that relates the polarization to the field is given by P is equal to chi E epsilon naught and the field. Epsilon naught we know, field we know. Chi E has got the name electric susceptibility. There's lots of similarities in a sense between the magnetic, we say magnetic susceptibility and so on, and here it's called electric susceptibility. If chi E itself depends on field, then it will no longer be a simple linear relationship between polarization and field. We will begin to get nonlinear effects. Okay. So chi E itself has got a field dependence that will add on to the field dependence here, and so we'll start getting nonlinearity in that relationship between polarization and susceptibility. Given that PE is equal to alpha E, we can then write that polarization is equal to n times PE, whatever was that average value, times n, and so we can then write it as n times alpha E. I'm simply substituting for PE here in terms of alpha E and the field. And we have n is again as before the number of molecules per unit volume. Comparing this equation with this equation, we can then write that chi E is equal to 1 by epsilon naught n alpha E. Comparing this equation with the previous one. So we have an expression that relates electric susceptibility to the electronic polarizability. I'll mention two terms here before we go on, free and bound charges. Note that what we have on the dielectric medium on the surface was QP plus QP and minus QP on the dielectric medium. These are what are referred to as bound charges, as I mentioned earlier. They can't migrate inside the field. You can move them farther apart, but the charges don't just move around inside under the applied field. They may separate farther or so on, but you don't change you don't move them around. On the other hand, what we had on the plates, say in the case when there was no applied field, even when you apply field, what is there on the plates, plus Q naught and minus Q naught, are what are referred to as free charges. They are coming from the source. The voltage source is supplying those charges, and that's why when we inserted the dielectric medium, a current begins to flow because the source is supplying extra electrons to compensate for the change in the charge that is being stored on the metal plates. Before we inserted the dielectric, I had the field, or I should say no dielectric, the field was simply V by D, which I can now express as Q naught by C naught, substituting for V in terms of Q and C, Q naught by C naught D, which I can also write as Q naught by epsilon naught D. Okay. Q naught by D, I'm sorry, Q naught by A, because I'm substituting here for C naught times D as epsilon naught A. C naught is equal to epsilon naught A by D is the relation there. So this term is what? We just saw it earlier. Q by A, surface charge. So we can write that since Q naught by A naught, by A is equal to simply sigma naught, I can then have an expression field is equal to sigma naught by epsilon naught. Okay. And I can then take this also, I will make use of this shortly, so I will write it also as sigma naught is equal to epsilon naught times the field. I will use this in a short while. Now after the dielectric is inserted, what do we have? The field remains the same. It is still V by D. But charge has changed from, on plates, has changed from Q naught to Q. In addition, when I had no dielectric, I didn't have any QP. So I've got additionally QP also built up on surface of dielectric. So basically, we can say that the charge on the plates changed from Q naught to Q to compensate for the charge that built up on the dielectric surface. Because when there was no dielectric surface, QP was not there. But now that you put in the dielectric medium, you've got a surface charge on the dielectric medium of QP. And so this change is simply given due to QP. So we can write then that Q is equal to Q naught plus QP. The additional charge that got stored is due to the presence of the dielectric medium. Now I divide throughout by A, the area. Q by A is equal to Q naught by A plus QP by A. And we've got sigma is Q by A. Similarly as sigma naught was Q naught by A and so on. Okay. And what sigma is the free surface charge density after the dielectric is inserted. So I substitute there sigma is equal to, and now when we go back, this is sigma naught, Q naught by A. And we just had an expression for that, sigma naught is equal to epsilon naught E. So I can write this as sigma naught plus sigma P and then make the substitution sigma naught is equal to epsilon naught times the field plus sigma P. Okay, just substituting for sigma naught there. Earlier we had seen that sigma P is nothing but the normal component. In this case, it's simply the polarization, right? The charge density is equal to the normal component, and in this case, because we are talking of the rectangular parallel plate situation, it's simply P. And we also had an expression for P in terms of susceptibility as P is equal to chi epsilon naught times the field. So what I can do is I can substitute here for sigma P in terms of P, and I can also substitute for P as chi E epsilon naught and the field. And so what I'll get is sigma is equal to epsilon naught 1 plus chi E. I make the substitution first for P, for sigma naught, for sigma P, and then I substitute P by chi E epsilon naught E and simplify it. Also given that our epsilon R is equal to Q by Q naught, that was part of the definition we had either Q by Q naught or C by C naught. We can then write that in terms of densities as sigma by sigma naught. Two areas are coming in there. And sigma naught is equal to epsilon naught E. We can substitute for sigma and epsilon naught E, and we will get then epsilon r, which is this, is equal to 1 plus chi E. Okay, you can make those substitutions. Substitute for sigma in terms of epsilon r sigma naught, and you can substitute for epsilon naught E in terms of sigma naught here. And so you can get then epsilon r is equal to 1 plus chi E. Or if you express it in a different way, in terms of polarization, polarizability I should say, we have epsilon r, I'm going to simply substitute for chi E, is equal to 1 plus n alpha E by epsilon naught. We had an expression for chi E in terms of polarizability. We just simply substituted that there, and we have this expression. This is what I was trying to get at in this lecture. If you remember, I said that this is something called what? The dielectric constant, or the relative permittivity, which is a macroscopic quantity. And alpha is a microscopic quantity which relates to the exact mechanism. In this case, it is alpha E, which is due to electronic polarization. So here we have an expression which is a macroscopic measurable that is related to the microscopic mechanism. So depending on the particular mechanisms that are there, we will have differences in this. And so we can find out by measuring maybe, and what are the mechanisms that are operative within the material. Next we will look at an equation known as the Clausius-Mossotti equation, and then I'll introduce few other things as part of dielectric materials. And we'll make use of these in actual materials, understanding the behavior of some actual materials. Okay? Okay, we'll close with that one.
So will you show the first few slides?
Yes.